like a HPC infra for quantum. There is a lot of discussion going on AI infra, like infrastructure for AI. Is this something HPC driven infrastructure for quantum?
Yeah, so this is a good point. I think, yes, I think there's on the hardware side for sure, because we need to make sure those work together. And I think the same thing counts on the software side as well. On the AI side, we're also seeing this is more not just about providing GPUs, but providing the software infrastructure around it. And I think we're seeing the same thing here. We're probably in a much earlier state than on the AI side. But yeah, I think at the end, we need to provide the right infrastructure, the right stack, that users can use it productively afterwards, yeah.
Okay. So let's give a big hand again to Martha. Oh, there is another question. Sorry, let me read. Thanks, Martin. Adam Moody is replying. So go ahead. There below.
Given the challenges of placing the QC in the same room as the HPC cluster, what advantage are gained in the QC so close to the HPC nodes? What time does a typical QC solve take to start to end? What's the fastest time? Yeah, this is a very good question. We get this question asked all the time, whether it's necessary to really put them so close together. And the answer is it depends. Some jobs really require this tight integration because they really have this really close feedback loop, and you're also using it to actually tune things as you go along. But some other jobs don't require it, right? Again, it depends on what technology you have, what the latencies are. In some cases, you also use this for error correction. So there are, for some workloads, I think, really good reasons for doing that. The other big thing that we have seen, though, in addition to all this technical stuff, it's a political thing. If you have it on the same system, tightly integrated, owned by the same people, with the same queue management, with the same user management, you can influence the scheduler much easily. You can have control over the system. If you send it to IBM or Rigetti over the internet, they have their own queuing system, and you have to wait until this comes back. So the idea of really owning the same system, tightly controlled, on the same floor, under the same user management, that's really one of the big kickers. And as much time itself, that really depends again on the technology and the size of the circuit. We have seen this from seconds, but people are also, you're running this up to 1,000, let's say 1,000 times. For some of the slower technologies, this can be in the range of several milliseconds, if I remember that, plus setup in between. The setup costs always some time. So it can be a substantial time that this runs. It's not just runs in a blink of an eye. In each individual shot will be quick, but in the sum, it will take some time. Does this answer the question, Adam? I hope so.
Okay. So let's give a big thanks again to Martin. So we'll switch to the next talk before the break. Will be presented by Professor Samir Shende. He gave a talk yesterday on the E4S stack, but today he will go into more on the tau performance systems. Professor Samir Shende is a research professor and director of the Performance Research Lab at the University of Oregon, and also the president and director of Paratools and Paratools SAS in France. He serves as the lead developer of the ES4 stack, tau performance system, program database toolkit, and HPC Linux. His research interests include scientific software stacks, performance instrumentation, compiler optimization, measurement and analysis tools. He served as the general co-chair for ICPB 2021 and the serving also the general co-chair for Europe Part 24. And he has been involved in a lot of conferences, as you would have noticed, and he's also handling this time ICPP 2025 as a general chair in San Diego. Chair, program chair. Okay, so let's welcome Samir again. I don't know. I know you from many years. I don't know when, since when. Okay.
Thank you.
Let's get started.
The slides are available on the website, and if possible, until what time should I go on?
We have time.
Okay. We may be able to even do a hands-on on tau as part of this. And sorry, it's not turned on. It's turned on now. Okay. So first, I would like to thank the Empathics team at the Ohio State University and the University of Oregon team on tau. And our motivation is that as our software gets more and more complex and uses hardware accelerator, it's getting harder to measure the performance of our applications on these complex systems. And the Tau performance system aims to deliver a scalable, portable performance evaluation toolkit for HPC and AI.
Your mic is off.
It's off. Okay, there. There. Okay. Okay. You can hear me, right? Okay. Okay, fine. Okay, so let me just say that Tau is a simple profiling and tracing toolkit. It can show you what your application performance looks like, and it easily integrates with application frameworks. The key takeaway that you should take away from this slide is that it supports many different runtime systems. MPI is our primary target, but also CUDA, ROCm, DPC++, SYCL with level 0, OpenCL, OpenMP, with a variety of different languages, support for hardware performance counters, and also third-party timer libraries. If your application already uses GPTL or CAM timers or FiProf or any of these other libraries, Tau can interpret those timer calls, and you will see that data flow into Tau profiles and traces. We have performance evaluation and analysis tools like Paraprof, Pprof. This is our website. But the most important thing is that to use Tau, you do not need to change your source code. You do not need to change your build system. You do not need to change your binary. You simply launch your application with a tool called Tau exec, provided some environment variables, some options. It generates the performance data. You can view it in tools like Paraprof, and that's what we will try to do in the hands-on if we get time. But here are the kinds of things it can show you. It can show you how much time is spent in each code region at the level of routines, loops. It can show you instructions executed in your code regions. It can access hardware performance counter data. And this is very important. It can show you how much time was wasted in an MPI barrier that was called implicitly inside collective operations. It shows you the MPI collective sync time. And you can see where that occurred and drill down into your code and then rectify it. It can show you memory usage, energy, I/O, and even scalability of your code. How do you use it? If you run your application with MPI run, you can just say tau exec-ebs before the name of the executable. That's it. It will show you the event-based sampling as well as the time spent in MPI calls. It will calculate the time wasted online, and you will be able to see that if you use GPUs, if you use CUDA, you can add a -kupti, a -ROCm for AMD. You even have a Python API so that you can say tau Python instead of Python. Once you generate the data, you can launch Pprof or Paraprof. Paraprof is the GUI. If you want to use tracing tools, we ship JumpShot with Tau. It comes from Argonne, but you can use Vampire by simply setting the environment variables like that and launching Vampire right after the application executes. We also support perfetto.dev, and you can see how to merge and convert the traces. So there's instrumentation, measurement, and analysis parts of Tau, where we can then support different languages and runtime systems. Essentially, instrumentation involves adding hooks to your code, whether it's done by source, compiler, or just preloading a Tau library. And we can target different runtimes, MPI with the PMPI interface, as well as the MPI-T tools interface, pthread, OpenMP, Level 0, OpenACC, OpenCL, CUDA, ROCm, Cocos. You get the idea. There's a lot of runtime systems targeted, but you don't need to change your code. You can simply use Tau, and it will allow you to target your codes, which may be using one or more of these runtimes together. But you launch it with tau exec, and this is how it looks. You can say tau exec rockum, and it will show you the performance of your kernels on the GPU as well as MPI. We have recently added support for hardware performance counter sampling on the GPU. So if you say ROCm PC, it will show you the PC samples and the assembly code where your application is spending time on the AMD GPU. If you're using NVIDIA GPUs, you can say dash kupti underscore PC, and it will do the sampling on the GPU side. Level 0 is the L0 for Intel GPUs, OpenCL, OpenACC. You can track I/O. OpenMP tools interface is supported, and you can use EBS for event-based sampling. And so you can use tau with the MPI-T interface to interface with MVAP-pitch. MVAP-pitch exports performance variables and provides control variables. Now, tau can get access to this through the bridge that is called the MPI tools interface. And then you can instantiate tau. It can generate the data on a per thread basis. And it also provides a plugin architecture. What this means is that if you want to write a different performance tool, you can tap into all the instrumentation hooks from tau by writing your plugin. It can be run with tau with no change to the binary, but then you can observe all the events that flow through tau, so you can make your own measurements based on that. And there are some plugin-based libraries that we provide, which can help you get recommendations, and you can control the usage of MPI resources. So you can customize such plugins, and there are some examples. Here is a list of the p-vars exposed by MVAP-H2 and control variables that are exposed by MVAP-H2. And you can see some examples of how we are using this to track the p-vars. Here is an example of an MPI collective sync dominating the runtime. This is the time wasted in an application inside an MPI barrier called by MPI bcast. It spent 365 seconds in this application. You can also see that besides MPI calls, there are COCOS calls, and the first argument of the COCOS parallel for or scan appears in the tau profile data. It also includes support for all the GPTL timers that were in this code, so you can see exactly which code region called, say, MPI wait all. And you can see in this view, the collective sync time is 428 seconds. 365 out of those came from MPI bcast, and 60 seconds out of those came from MPI all reduce. And then you can drill down to those locations and see exactly where it was spending time. Here is an example of comparing collective sync time in Hefty. This is collaboration from our NSF-funded project. And you can see exactly the difference between the MPI wait all, MPI all-to-all time and the time spent in MPI collective sync across two different ranks with this. Here is another example where some nodes are spending a lot of time in this MPI barrier, while others are not in this collective sync. And this is another application we are working with. This is AWP ODC, and you can see the time spent in kernels running on the AMD GPU, and you can see the exact time spent and where it is spent in the line of source code using call site profiling in tau. We also support perfetto.dev like this, and instrumentation of libraries. So we can rewrite binaries and rewrite shared libraries like libhdf5.so and simply generate a profile file which has, say, HDF5 functions. Here is an example of Dynast API working with AWP ODC, where you see the internal names of the functions. This is interesting because this is an MPI application and we just pick up the application binary, rewrite it, and all its function calls get instrumented. We have a filter file as well. So you can see internal function names as well as CUDA calls. And with that, let me just show you how this works. You can see these slides later. You don't need this. Some of you have already seen this AWS setup that we used for the hands-on yesterday. You can just log into this, use this code 70034. These slides are on the web. This is slide 53. Just put in that code. You'll get a 6-digit email verification code, a 2-factor authentication code. You'll be able to log into one of these clusters, open a remote desktop, and then you'll get a screen like this, open up a terminal window, and just run a code with Tau. So here is an example. You can go to the PETC directory, PETC CPU, and just build it, compile it, and run it. Let me just show you how that works. And here is the example. Here is the example. I'll go to, say, PETC CPU, and I can just say compile.sh, and it will compile the code. Let me say make clean, clean.sh, compile.sh, and it's compiling the PETC application. I'm just going to go here and say tau.qsub, and you can say qsub tau.qsub, and it will run it like that, and I can launch paraprof once it runs, and then it can show you the time spent in all the PETC calls. It will show you the key performance, and you can see this like that. Okay, so here is tau.qsub. If I don't want to wait, I will just take this and run it right on the compute, on the login node like this, and generate the performance data and launch paraprof here. So here, if I click on node 0, it can show me the time spent in different MPI routines in the internal PETC calls that we have here. And I can click on each rank, and it can show me the, say, thread statistics table, where I can expand this, and see how much time was spent in which code region. So paraprof is the profiling tool. I can look at this and see where it's spending its time in, say, MAT-LU factor. Let me show you some other examples of using Tau. Here is a code called CoMD. I'll go to the src MPI directory, make clean, make, and then go to the bin directory and cat tau.qsub, and just say, you see, this is the comd.qsub. This is how I run it. I just added tau exec-ebs before the name of the binary. That's the only difference between these two batch submission scripts. They are running on 2 nodes. They are using mvapich, and this is all running on AWS. When I say qsub tau.qsub, it will run, and then it will generate profile data like this. So I can launch paraprof. I can open up a node and say, show me the thread statistics table. If I click on this, I click it again, I can go down here, look at the names of routines. So in this case, you can see that most of the time is being spent in this function called ljforce. Out of the 25 seconds, 23 seconds are spent here. I can expand this. It will show me line by line breakdown of where time is spent in LJ Force. I can right click here. I can say, show me the source code. And it will say this line of code at line 198, which is in about 5 for loops. It's nested. This is how much time was spent in this line of code. So I can see the MPI performance. I can see the time spent in individual lines of code. I can see that this is the function that really matters. These other functions don't matter as much. I can see the MPI collective sync time, which shows me the time wasted in a barrier within a collective operation. And I can if there was a send receive call, I can go inside this call. I can see where samples are getting taken and what this call was doing internally. And so this is a good way to look at the performance of your application across different ranks, and you can see where the time is being spent. Here are some other examples. Let me just PETC CUDA and just launch with Paraprof. You can see here, this is the time spent in MPI. If I go down to a particular thread, if I click on thread 2, it can show me the kernels running on this NVIDIA GPU on AWS on the compute nodes. I can right click here, say, show me the function bar chart. It can show me the threads. And you can generate profile files. You can generate trace files. And here is a trace.qsub where you can merge and convert the traces. Then you can launch Firefox and go to perfecto.dev like this. And perfecto.dev is a tool from Google. I can click on the trace viewer, open the UI, and then I can load a trace file like this, a JSON file, and it will show me the 4 MPI ranks where CUDA calls are being executed on the GPU. I can click zoom in. I can go to widen W and go right down to a particular CUDA call here and see what the rest of the MPI rank was doing at that point. This is a foo-sparse CSMV kernel. You can see the flame graph, which shows you what PETC timers are active when this CUDA call was executed, and the MPI performance across the application. I can shrink this like this. So there are interesting visualization tools that Tau provides. You can even go to the Tau directory and run a paraprof on demo.ppk. Here is a profile file. I'm looking at loop data. I can see the function bar chart. But more interestingly, I can see the 3D graphics by going to Windows 3D visualization. And it shows me the shape of the profile. Here, I can zoom in, I can zoom out, I can rotate this 3D profile. This is all running on AWS, by the way. And I can see that there are 2 functions. One is the inverse of the other. They combine to make the full. You can see the 2 halves of the machine in a slight different shade of yellow. I can use a bar plot. I can see that there is one CPU that does something different from all the other CPUs. And I can move the sliders for the function like this, and the thread like this. And you'll be able to see there. Where they intersect, what is the value in the 3D graphics with 129 seconds. Scatter plots show you the maxima to minima for MPI barrier, 3 different functions here, and a color function. So you can see each rank has a unique ball over here, and they are color coded. So there is this one thread that is different from all of them. And you can see the 2 of these have a -1 correlation coefficient. As the time in one increases, the time in the other decreases. So this is just a quick overview of tau. Reach out